Hey everyone, I'm Hussein. I'll be presenting KZH-fold today. So before jumping into the paper, let's review some necessary backgrounds and definitions. So first define what an argument of knowledge is. Assume we have an MP language such that a verifier has an instance while the prover has the instance and its corresponding witness. So in an argument of knowledge, the prover and the verifier basically interact with each other, and at the end of the protocol, the verifier is convinced that the prover actually knows a satisfying witness. Finally, we call an argument of knowledge non-interactive when basically the interaction is a single message from the prover to the verifier. And in this case, we call it a NARC, which stands for a non-interactive argument of knowledge. So, okay, next I want to demonstrate IVC or incremental verifiable computation. IVC is a specific type of argument of knowledge used to prove iterative computations, as you see in the diagram. So in these computations, we are iteratively computing a function f such that input to each step is the output of the previous step. And PCD or proof carrying data is a generalization of IVC, which enables parallel or distributive computation. So currently, the state of the art of IVC PCD schemes are built from accumulation schemes. So let's quickly define what an accumulation scheme is. In a high level, assume we have two MP languages, LPI and LAC. An accumulation scheme for these two is an interactive protocol which reduces satisfiability of an instance of LAC and an instance of LPI into a single instance of LAC while satisfying properties of completeness and knowledge soundness. So completeness basically means the resulting accumulated ACK prime is a satisfied MP statement if and only if ACK and pi were satisfied MP statements. By the way, when I say the decider, I am basically referring to the satisfiability function of NP language LAC. And knowledge soundness in a high level means given a witness for ACK prime, there exists an extractor that given the witness for ACK prime outputs a witness for X and ACK. Okay, so far this has been the standard definition of an accumulation scheme. But another property we are particularly interested in this paper that I will later illustrate the motivation behind it is sublinearity, which basically means the following. So first, we want the size of the statement in uh, the statements in language LAC to be sublinear in terms of the size of the statements in the original language LPI. And second, we want the decider time for LAC to be sublinear in the verification time of LPI. We will later see why this sublinearity is important for us and what it means in concrete numbers. So next, I want to quickly point out the BCLMS compiler, which shows how to build an IVC or PCD scheme given a NARC and an accumulation scheme for the NARC verifier. I'd like to highlight the two following properties of the resulting IVC PCD scheme, which is our main motivation actually to build a sublinear accumulation scheme. So first, the resulting IVC, basically the IVC proof will be equal to the accumulator size. And secondly, the verifier of the IVC will be essentially running the uh, accumulation scheme decider internally. So what this implies is that when we utilize a sublinear accumulation scheme, the IVC PCD proofs are going to be sublinear uh, in terms of the original IVC statement. For example, the function f, which is our step function that we were like trying to iteratively compute, and verifying the IVC proofs will be also sublinear. And with this motivation, we built a sublinear accumulation scheme. So later, based on that, with the BCLMS compiler, we can build IVC or PCD schemes with sublinear proofs and verification. Okay, and just to demonstrate what happens when we use a linear sized IVC, consider the concrete example of Nova, which is a linear sized IVC scheme. If the circuit F is of size 1 million R1CS constraints, which is a fairly moderate size, it basically results in an IVC proof size of 80 megabytes, which can be verified on a consumer grade laptop in around 4 seconds, which is very non-ideal, especially in the distributed setting, as I will demonstrate. And previous work such as Micronova and Nova try to solve this via running the IVC verifier within another ZK snark, which has sync proofs, and they basically succeed to reduce the proof size from 80 megabytes to around a kilobyte. However, this does come with serious downsides. So first of all, the resulting proof is no longer incremental, and secondly, the cost of this ZK snark compared to a single step of IVC is around 24x, which basically means high prover overhead. Okay, so next I want to talk about PCD. So PCD is like a widely used framework for distributed proving. And what, uh, in essence, so when one prover wants to delegate part of the computation to another, they basically have to generate and send a PCD proof. If PCD is built on top of an accumulation scheme, this proof is essentially an accumulator. And the receiving prover must then verify the PCD proof to ensure that the previous prover did not cheat. And as a result, the system's computation overhead is primarily determined by the size of the accumulator, and the additional latency is introduced by the verification step each time that the computation is essentially passed along. And concretely, when using a linear size accumulation scheme, both communication and the system latency will be high as a result of high accumulator size and high verifier time. So ideally, in a distributed proving setting, we'd like to use a sublinear accumulation scheme. Okay, so that is the background and our motivation for building a sublinear accumulation scheme. Now let's get into the paper. So our contribution is as follows. First, we introduce a new polynomial commitment scheme with optimal opening, called KZH. And just a quick note, KZH has applications beyond accumulation schemes and IVC. For instance, a recent work Iron Dig building on KZH, they built a transparent dictionary, uh, which shows that KZH can be useful as a standalone primitive. Next, we built KZH-fold, which is an accumulation scheme for KZH. So at a high level, KZH-fold enables aggregation of multiple KZH verification statements into a single statement. Using the sublinear accumulation scheme together with the generic BCLMS compiler, we then construct an IVC PCC scheme that achieves both sublinear proof size and verified complexity. As a concrete application, we show how KZH-fold can be used to design a signature aggregation scheme for Ethereum to basically reduce the finality time, which is around 15 minutes right now. However, due to the time constraints, I will not cover its details in this talk. And finally, we present new approaches to non-uniform IVC and non-uniform PCD. It's noteworthy that our non-uniform PCD scheme achieves the state-of-the-art in terms of the prover efficiency, and it's independent of KZH-fold, meaning it can be initiated with any polynomial accumulation scheme. However, for the sake of lack of time, I will not be also considering the non-uniform versions of IVC and PCD in this talk as well. Okay, so KZH, which is our polynomial commitment scheme, to give you a quick overview, we basically construct a multilinear polynomial commitment scheme. So suppose L is the size of our Boolean hypercube, in which the multilinear polynomial is defined on. So in terms of the efficiency, the commitment time basically requires a linear number of group operations in terms of L. Concretely, it's two MSMs of size L. The proof size scales as a square root in terms of L, and the verifier time is essentially dominated by a multi-pairing of size L, multi-pairing of size square root of L. And then we extend KZH to KZHK, where we basically reduce the verifier cost from square root to K times N1 over K. And this reduction in cost does come at a higher commitment cost. And then building on KZH fold, we construct building on KZH, construct KZH fold, which is our accumulation scheme for the KZH verifier. So the very basic observation is that the KZH verifier function essentially consists of degree 2 scalar multiplications plus degree 1 pairing. Now, using the generic Porosar compiler, we build an accumulation scheme for it, uh, such that the accumulated size for KZH has a size of square root, and the decider complexity is also square root, which is again dominated by a multi-pairing of size square root. This is essentially important for us, as I have illustrated in the slides of the BCLS compiler, since the accumulated size will be reflected on the IVC proof size, and the decider complexity will be also the IVC verification time. And finally, we also generalize KZH-fold to KZHK setting, which essentially building a folding scheme for KZHK instead of KZH would lower our accumulator size and decider from K times n to the power of 1 over K rather than square root. And this does come at a cost of higher recursive overhead, which we have found to be uh, a very useful trade-off in practice in our implementation. And finally, let's see some concrete numbers. So we have implemented our scheme and compared it against Nova. Concretely, for a circuit of size almost a million, as we expect, we get a almost 3x prover overhead compared to Nova, while our verifier time is 50x better and our communication is 2000 times better, which is a huge improvement going from almost 80 megabytes to 40 kilobytes. And that's especially important for the distributed setting, as we have previously discussed. And thanks for listening again.